I will speak about crossing symmetry of superstrings amplitudes. Okay, so crossing symmetry is very linked intimately to string theory since the beginning, because it was one of the main assumptions that Veneziano used when he wrote his amplitude, which we know lead to the birth of string theory. And so with Corinne Delacroix and Ashok Sen, we could study rigorously crossing symmetry of superstring amplitude at all loops. And we managed to do it roughly 50 years ago, so it's kind of a nice birthday gift for the Veneziano amplitude. And I will start by reviewing already a few restrictions. So the first is that it will be the crossing symmetry just of 4-point amplitudes and of stable states. So in my opinion, it's rather like technical assumption which are also present in QFT. So if you can solve this in this case, you can also generalize the proof in QFT. But for now, we restrict to what is already known in quantum field theory. So just to summarize briefly the main ideas. So crossing symmetry, it's relations between amplitudes with exchange of particles and antiparticles in initial and final states. And the point that it's often assumed or observed. So in most textbooks, you will see, like we see obviously that at tree level or maybe one loop, it looks crossing symmetric. Or you will use it and then derive relations for amplitude, like in the recent scattering amplitude program. So the question is, why do you want a general proof? So the first is that to be sure that the observed examples are not accident, because the amplitudes are very simple. So for example, if I ask you to show that an 4-point amplitude at 100 loops is crossing symmetric, I think you will have some hard time to show it. So it hints that it would be good to have a very general proof and to really spot what are the assumptions for such a proof. And the second interesting point is that the assumption you need to prove crossing symmetry are intimately linked to fundamental properties of QFT, like causality and locality. So if you're able to find, to say something about crossing symmetry, you can also hope to make some statement on causality and locality, which in the context of string theory is very useful because we don't really have a position space representation, as I will comment more later. So it's not obvious how you can define locality, and intuitively we know that locality cannot strictly hold in string theory because you deal with extended objects. So the question is how these two notions appear in string theory, and so one way to attack the question is instead to prove crossing symmetry by some other mean, and then you know that there is some relation with these two notions. So the question will be to make this clearer, so this we don't have, but at least we know that in some sense string theory has some notion of causality and locality. So here is the idea of the proof in QFT, which is due to Bros, Epstein, and Glaser, so in 64 and 65. The first point is to prove analyticity of the S matrix in what we call the primitive domain, delta. Then you find that the analyticity is not sufficient for proving crossing symmetry. So you need to do an analytic extension, which you call h of delta. And then you can show that the second point will imply crossing symmetry. So this is a program that these people did. Some remarks is that the point 1 is non-perturbative in their papers because they deal with a full S matrix. So it was this old constructive S matrix program. And it's also because of that they need to assume that you have a mass gap, because otherwise analyticity is not a very well-defined notion. And they didn't want to really speak about Feynman diagrams or these kind of things. And interestingly, the point 2 and 3 are very general statements from the theory of several complex variables. So this will be useful for us because in string theory we can prove one perturbatively, and because we know that the point 2 and 3 hold for any function sharing the same properties, we can just directly use the result these people derived and find crossing symmetry from the analyticity. So then, why also it's interesting to use analyticity, especially in this primitive domain, is that this primitive domain is a starting point for many other results. So in particular, you can show very easily that you get analyticity in 2 other domains. So the just-Riemann Dyson and for elastic forward amplitudes. And in general, it's also something that you can use as a starting point for other properties that you can find interesting, like dispersion relation, positivity bonds, and the CPT theorem. So the main idea of this is that we will consider, so first I will review in QFT how they did the proof and why in string theory you cannot just say that it also works. So then we'll generalize the proof of Bross-Epstein and Glaser to work with a more general QFT. So this more general QFT will include string theory, but in principle you can also consider more general QFT if it fits in our assumptions. And so, yes, so let me start with QFT. So first I will introduce just some general notation to really make precise what I mean by crossing symmetry and the analyticity. So let's consider a 4-point scattering process. So later for the analyticity I will generalize to n point, but just to be more concrete, let's do 4 points. So we have formed external momenta PA, which are in general taken to be complex. We have momentum conservation. And in some cases, so when we want to make contact with physical amplitudes, we need to go on shell. And then we have a series of objects you can define. So first you start with off-shell green functions. So in the case of QFT, you will compute this as a sum of Feynman diagrams. And from this off-shell green function, you can extract the truncated green function. So you strip the propagators of the external legs. And once you have removed this propagator, then you can go on shell. So, okay, so in the constructive S-matrix program, they will work directly with this object. So now the point is that this just going on chain is not sufficient because you know, due to kinematics, not all values of momenta being on shell lead to physical amplitudes. So for that, it's useful to introduce the Mandelstam variables, so STU. On the mass shells, they have a relation which links them, so just 2 of them are independent. And you can very easily define the physical region in terms of these Mandelstam variables by taking one to be bigger than the sum of the mass squared and the 2 other being negative. And then you can look at the physical amplitudes by taking the momentum to lie in one of the 3 regions. So in terms of a graph, it's, here is a ST graph, and so the slashed lines denote some special values. So in particular, U equals 0 is here. And so here you see that, for example, S is bigger than the sum of the 4 masses, T is negative, and U is negative, so negative U goes in this direction. So it's the S physical region. And what you find in this diagram is that obviously the 3 physical regions are disconnected. So you have 3 different amplitudes, but a priori you cannot go from one to the other by being like physical and on shell. Okay, so here is the statement of crossing symmetry. So the processes STU, where you take 1 and 2 going to 3 and 4 for S, and for T and U, you exchange 1 initial particle and 1 final particle, and you take the, you consider antiparticles instead. And all the CPT conjugate are equivalent under analytic continuation on the complex mass shell. So in particular, you have the amplitude in the S region in terms of S and T, is the amplitude in the T region in terms of T and S. So you just have to exchange them. So here 2 points are important. Is that first we consider so it's really under analytic continuation and on the mass shell. So this crossing symmetry looks very natural from LSD, you will say, because all the A, S, T, and U come from a single function A, which come from just off-shell green function. So you would say it's obvious that everything comes from a single function, and I just have to continue the argument. But the main problem is that here the physical region, as I said, are disconnected, and you are not sure that this original function A or even the G are really analytic on all the domain you need. And also that you can find an analytic continuation from one region to the other while staying on shell. So for example, you can find some generic off-shell analyticity. But here you need a bit more. So it's why LSD, in fact, like it helps to think about these conditions, but it's really not sufficient. You need more. And it's also the idea that when you look at a function, what is important is not the functional form of the function only, but also its domain of definition. So if you have two functions which look the same but are defined on completely different domain or space, you will not say that it's the same function. So here it's this is what translates this condition. So now here is the outline of the proof in QFT. So this first paper was doing it for the 4-point, and in this fifth paper they proved some general analyticity condition for n-point, but could derive crossing symmetry just for 5 points. But they had to assume some additional conditions, so it's why I prefer to leave 5 points aside for now, and we focus on 4 points. Sorry? Does not apply to massless particles. No. So I will mention briefly what we do with massless particles after. So
just to be sure, the difference between the LSZ and the analytic continuation is the LSZ as physical, not physical, real momenta, but off-shell.
So you can take them.
But here you have the off-shell constraint, but complex momenta.
Yeah, but so the green function from LSD, you can also consider complex momenta in general. It's just that you're not sure it's analytic, and it's not sure you can do analytic condition from one region from the other. So like it could be well defined in the physical region when you take the limit of the PA from complex to the physical region. But can you find a path where there is no singularity between different regions? This is not clear from LSD. So it's the main difficulty. But LSD can be defined for complex momenta and.
Because LSZ is defined for real momenta.
I think you can take it. You can use it for any.
But it is you can simply take a section where all momenta are real, but you get different limits on this real section. While in the analytic axiomatic, you get a you consider complex extension. This is what we're
Yes. So, okay, so the first assumption, as I said, that we need to assume that you have a mass gap, and the asymptotic states must be stable particles. So then we define the primitive domains. So first, let me define the A of alpha. So it's a subset of 1 to n. So here now I'm looking at n-point function. P of alpha is the sum of the momenta indexed by this number. And M alpha is a production threshold corresponding to this momentum. So now from this, we consider this set of domains, where you consider all the possible subset of integer, and you have 3 different conditions. So let's start by the last one, which is the simplest. So the last one tells you how many of the components of the momenta can be complex. So if k is 2, for example, you can just have the time and one spatial component to be complex. If k is d, all the components can be complex. So here it's really just a restriction on which momenta are complex and which one are real. And then here you have 2 different conditions. So the PA can satisfy one of the 2. So the first is that if the imaginary part of PA is not 0, then it should be a time-like vector. If the imaginary part is 0, then the momentum square should be below the production threshold. Okay. Then, so what people did in the early 60s is to prove analyticity inside the delta of D. So it's really the generic case where all the momenta are allowed to have complex components. Using microcausality, so it means that fields commute at space-like separations. So you can start with your green function in position space. You impose this condition and you try to see what it tells you in terms of the momenta. The main problem is that this domain has no intersection with the mass shell. So if you view what we want to do for crossing symmetry, we need to find some bigger domain. And the question is that is it a good starting point? And what the Bros, Epstein, and Glaser found is that it's indeed good. So they computed the envelope of holomorphy of delta of 2. So you can, it's just basically analytic extension. And what you find is that this edge of delta 2 then has a non-trivial intersection with the mass shell. So the last point is to try to find a path connecting the different regions. And I could also...
Delta 2 is when you allow P0, P1, P4.
Yes, yes.
So the
light cone, basically, yeah. Okay. Yes. So, and then they finally show that there is a path in this edge of delta 2 inside the mesh shell and between all pairs of I epsilon neighborhood of physical region. So here it's also interesting because I don't really connect the physical region, but they can get close to I epsilon. And in fact, this I epsilon, you can link it to the I epsilon prescription that is usual in QFT. So some notes. So here, interestingly, only the edge of delta 2 is necessary. So even if they started with analyticity in delta of D, they didn't need the third domain. And it's useful for us because using string theory, we could prove analyticity just in delta of 2. And then the points 4 and 5, as I said in the introduction, it's a consequence of the theory of several complex variables. So this, we don't really have to do it again. And in their case, they worked with a complete S matrix. Okay, so here is a very short proof that you don't have an intersection between the primitive domain and the mesh shell. So if you consider the complex mesh shell condition, you get these two relations. And if the imaginary part of PI is time-like, then you find that the real part should be also time-like here to have a chance for this condition to be satisfied. But then this first condition tells you that it's not possible because two time-like vector has a non-zero inner product. But then if you consider the imaginary part to be 0, you will find that the PA are below the mass threshold. So here it's a first quick point to give some more intuition about this domain. Then a second note on the envelope of holomorphism, so to explain more why the point 4 and 5 are independent on the function. So the point, it's a bit like when you go from a function of one real variable to one complex variable, the function, if they have to be analytic, they are much more constrained than just like a differential function of one real variables. But when you start to have several complex variables, it's even stronger. So if you consider a function f of n variables, which is analytic in delta, you find that analyticity in several variables, so the 1 to the n, constrains the shape of delta. And so as a consequence, it means that if the shape is not arbitrary, then the analyticity in delta will, in general, means that you are analytic in a bigger domain f of h of delta. And the very important point that this h of delta just depends on delta, not on the function f. So it's really a question of geometry. It's not even analysis anymore in some way. And so typically they used this edge of the wedge theorem that I will not describe more, but if you are interested, there is a nice Wikipedia page, for example. But the main point is that like you can reduce this question of finding the good domain just to geometry at the end. Okay, so now I will go to crossing symmetry for string theory. And so I think now everyone is aware of what is string field theory, and I don't have to motivate it. But because these points will be important for the discussion, let me remind it quickly. So string field theory is a standard, you can see it as a standard QFT with an infinite number of fields, an infinite number of interaction, and non-local interaction, which are proportional to the exponential of minus k squared. And they should reproduce the worldsheet amplitudes. So now, because of non-locality, we cannot use a position representation. So we can also not use assumption from local QFT like microcausality. And because of that, we cannot derive analyticity like in standard QFT and using the work from the early 60s about that. So we have to do it again. Using some other way. So the way we do it is to study singularities of green function by studying the Feynman diagrams in momentum space. So we directly derive analyticity in momentum space, and then we find that it's analytic in delta of 2. So, okay, just to set a bit the notation and explain more from why it's I mean, you have this you have this expansion of k squared. So first, you can do a string Fourier expansion of the string field. So the phi a of k will be the spacetime fields, K is the momentum of the center of mass, and it is d-dimensional, where d is the number of non-compact dimension. And A is discrete indices, so Lorentz indices, KK modes, and so on. So the general form of the 1pi action is like this. So you have a kinetic term, and then some of vertices, so interaction, endpoint interactions, with some very generic coupling tensor. So here the propagator will work in a basis which is a eigenstate of the momentum and also of the mass. So typically, so in this way you can very easily read the singularity of the propagator. So they are just given by the mass of the particle propagating. Here QA is some polynomial, and MAB is the mixing matrices of states of equal mass. Then you have the vertices, which are a bit more complicated. So here you have some integration over the moduli parameter, but we don't need to be more specific. Here you have some polynomial of the momentum, and depending also on the moduli parameter. But the important point for us is this exponential factor. So first you have a damping factor, which ensures that when you sum over many states in internal legs, you will converge, because C can be made arbitrarily large, and MA depend also on the index of the particle. And then here you have some matrix Gij, which couples to the, multiplies the two momenta. And the point is that this Gij is positive definite. And because of that, you see that for spatial momenta, you get a minus sign, so this converge. But for time-like momenta, this will diverge because you will get a plus sign. So this you will have to take care about it, and it's at the end because of that problem of the time-like direction that you cannot go back to position representation. Okay, so now using these vertices and propagator, you can find that so truncated green function will be sum of Feynman diagrams, where each diagram has this generic form. So again, you have some integration over moduli parameter, an integration over the loop momenta, and then you have a exponential where you have loop momenta and external momenta. You have some polynomial in the momenta, and finally you have also the propagators in 1 over k squared plus m squared, where k are the internal momenta, and you can see them as linear combination of the loop external momenta.
So you are considering not only one particle irreducible, but
yeah, so here it's more like I'm moving from 1pi to more a generic description of loop amplitudes.
so you have internal and loop, so it means that you...
Yeah, exactly. So it's not 1pi anymore. 1pi was more to just give a very condensed notation, but yes. So, but exactly, yes. Okay. So, and as I said, because of this big GRS is related to the small g of the previous slide. So it's also positive definite. You can show this. And then the integral over the loop momenta will diverge in the energy direction, and they will converge in the spatial direction. Okay, so now to solve this problem, you have to generalize the weak rotation. So this was done by Ashok and Rogipius. So first you define the green function for Euclidean internal and external momenta. And then you do an analytic continuation of the external energy and of the integration contour, such that you keep the poles on the same side, and you keep the end of the contour at plus minus infinity. And so here I could show that in this way the amplitudes are analytic for spatial component trio and energy in the first quadrant. So here it's a picture that I think now everyone has seen, where you start by integrating over the Euclidean energy. And when you do the analytic continuation of external state, the pole will move, and so you deform the contour such that you keep on each side. And so using these prescriptions, I could derive a Kutkowski rule, unitarity, spacetime, and moduli space epsilon prescription. And let me advertise that, in fact, if you want to define the time-like Liouville theory properly, you also have to use this prescription. So the paper should appear soon, hopefully. Okay, so now here, using this prescription that we try, we could prove analyticity in delta of 2 of endpoint superstring green function at all loops order. And from the previous works of Bross, Epstein, and Glaser, this implies crossing symmetry for n equal 4. So here are some comments. So first, we work with Feynman diagram, so it will be a perturbative proof, contrary to the original proof. It's valid for states with any spin. There are 2 technical assumptions that we have a mass gap and stable external particle. And to reach this, we need to regularize the mass state. So the way we did it is that the simplest is to insert a projector over the mass states and consider the part of the amplitude where all the mass states have been projected out. And in this way, this part of the amplitude has exactly the same properties as the amplitudes people were looking at in QFT. And it also means that the part of the amplitudes for which we cannot prove analyticity or say anything is exactly the same thing you would get in normal QFT. So then the problem of completing the proof for mass state has nothing to do with string theory, but it's just a QFT question.
So you are projecting also in the
internal mass states, yes. And in practice, so for the external one, you can consider putting some small mass.
So it is a kind of Wilsonian action you are considering?
I guess you can see it in this way, yes, yes. Yes, because also even when you use this projector, because it commutes with the BRST charge, I think, then you can still define this, like the BV equations, and I mean, it's still you still have a good control on this part of the theory. And so, okay, so here the envelope of homomorphism is only for n equal 4. And by using all this, I mean, technical assumption and the regularization, it basically puts the proof at the same level of QFT. So let me stress that any difference is a matter of QFT, not string theory. So very shortly, the way we were finding the singularity is that we start with some PA for which everything is well defined. Then we find a path between the PA we started with to the one we want, so in the domain where we want to prove analyticity. We deform the integral contour as the poles move. We assume that there is a singularity, so typically it's when 2 poles from opposite sides collide and you cannot deform the contour. But then you show that you have an inconsistency, so it means you cannot get a singularity while you deform the contour. And we do it in 2 steps. So first we prove analyticity in delta 1, and then we go from delta 1 to delta 2, and in both cases you can show that if you assume you have a problem, in fact you find that the momentum cannot be in delta 1 or delta 2. So this shows analyticity in these 2 domains. So now let me conclude. So what we got first is analyticity of superstring endpoint amplitude in delta 2 at all loops order. Then we have a proof of crossing symmetry for 4-point superstring amplitude, which is at the same level as QFT. This also shows that in some sense string theory behaves like a local QFT, at least for the aspect of crossing symmetry, so it's not completely widely non-local. This also will give a new proof of analyticity for more general QFT than what was considered before. And it's the starting point for studying other properties. So in particular, there is 3 very direct things to look at. So you can try to prove the CPT theorem by generalizing the arguments that people used in the past. There is a question like, can you prove analyticity in delta of D also by generalizing the method we have? And another point which would be more satisfactory is to prove analyticity in H of delta 2 directly from Feynman diagrams and QFT techniques, and trying to avoid this very heavy mathematical machinery. And on this, I will thank you for your attention. I don't think we can really say it's completely local in the sense that you still have the exponential interaction in the so you still have the exponential of chi-square in the interaction. Yeah, but I mean, if you go to position space. Yeah, but I mean, if you have an exponential of the Laplacian, I will not really call this a local theory.
Yeah, this is an consider, say, non-point object scattering of brains or something like that? I don't know.
Yeah. I mean, the point is that if you look just at basic excitation, you don't really see difference with QFT. I mean, with respect to this analysis, at least. So, I mean, it's not that it doesn't affect, it's that you can also find another, so you can still consider a master equation, which will encode still the gauge invariance and nice properties. So, for example, the amplitudes will not hook gauge invariant, so you will find some problems here, but you still have some BV equation telling you that everything works. I mean, it's still consistent. So the point that any theory that matches the structure I wrote is contained inside. So I would say, like, if the open closed string field theory matches these properties, it will be contained.
Did you assume supersymmetry or Minkowski space-time?
So supersymmetry, no, and Minkowski, no. So I think so. We assume that the background metric is Minkowski, but you can consider that. I mean, nothing tells you that the graviton cannot be an excitation in the spectrum. So I mean, it's like in standard string field theory where you still fix the background, but in principle gravity is there as an infinite sum of interactions. So we don't.
Some problem defining S matrix and momenta. If you start playing with the background, defining the ring, outstate and momenta are very it's very subtle. Yes. Yes. You say it's got. I don't complain at all. Otherwise, because but then you do a lot of recalculations, right? In order to prove
this. But this, I mean, this weak rotation in this more modern perspective, in some sense, it's more formal. It's just that you have an object that computes something in Euclidean signature, which you interpret just as a function of complex momenta. You want to get Lorentzian momenta, you just do some procedure to go from one to the other. So it's really a definition. So you start with something which is well defined, and you want to compute something that if you were trying to get it directly, it's not well defined. So you just define by this analytic continuation. But you don't really have any more interpretation as in flat space or these kind of things. It's a bit like the Lewis theory I was mentioning. If the different starting point, it's really formal. It's if you want to define UV theory with the external states, you want to, you see that it doesn't make sense. So you start from something that makes sense, you continue, and you just say, here is my definition of the theory.